I think I would like your participation. So just be active as much as you can. And towards the end of the day, and you eat lunch, so you must be very tired also. So anyway, let's keep going. So the module, this module, we're going to talk about alternative renewable energy sources and hydrogen derivatives. We already discussed a bit. So I think the whole course, what we have my plan. I know that don't forget ACWW. Obviously, that's the final thing. Maybe you'll ask in your exam. I don't know whatever exam they take. Hopefully, that's not too difficult. I don't think that will be. So basically, one is the steel industry because we have a lot of participants. In Durgapur is a steel city. Power, because power is also relevant. And a lot of our colleagues come from power industry. So those two areas that I was going to cover. And then decarbonization. Decarbonization. One thing is that what are the strategies to do that decarbonization? But before that, how to calculate, how to account the carbon accounting. So that's life cycle assessment. I think broadly these are the things I'll be talking about. And one of the key solutions to hydrogen, definitely, because otherwise countries couldn't spend, companies couldn't spend billions of dollars around the world. So it must have some legs, but it's not only solution. And as I said, you can ask me any question about hydrogen. I probably will answer. So, but yeah, if I cannot, I can refer to colleagues, and there are a lot of information nowadays. Suddenly, hydrogen became one topic. So you look at, I know from the back a little bit difficult to. So this is not the kind of process from biomass to hydrogen. You can get hydrogen from many sources. So they are saying biomass, when you wood or whatever biomass you have, you dry it and then gasify it, product gas, you clean it. There are PSA, called the pressure swing absorption system, and you can clean it and you get really hydrogen, clean hydrogen gas and store it. Because hydrogen is a component what I sometimes define, photosynthesis activity wood. Wood is basically, or we have got a tool in front of us, wood is basically CO2 plus water in the presence of sunlight. And what else I think you have got? Trees can make it, obviously. The biomass is essentially CO2 plus water in the presence of sunlight. And that's photosynthesis, isn't it? That's the basics and foundation of life, essentially. So wood is nothing to me, that's CO2 plus water, because that's what I call carbohydrate. And that carbohydrate H is there, so maybe 6% or 5%, whatever quantity is there. That's the amount we're trying to extract. Because what's the benefit if you get hydrogen, all the carbon elements, everything fall behind, keep behind. You use hydrogen, and if you make power, it becomes H2O is the byproduct. So that's the instead of CO2. So that's the kind of work we're talking about. So International Journal of Hydrogen Energy, that's one of the key journal in that research journal in that space, and I publish some of the journal. And that's through our PhD work. So technical, environmental, economic assessment framework and tools for low emission hydrogen production. A case study from Australia, Mohammed Khan. So he was one of my PhD students, sponsored at University of New South Wales. He did a good job. He already working there as a scientist or a researcher postdoc. So I have published that. So he's from I think Pakistani, and also Venkat Balasubramanian. He's from South India, obviously. He was another my student, and he finished technical evaluation of integrated green hydrogen system. So these two PhD project finished already. They are working as researcher, but other students are working on. So through these kind of activities, we develop a lot of tools, and that's not only PhDs, but other mechanisms to develop in that kind of capability. So obviously, life cycle assessment for energy technology, issues and challenges for conventional and hydrogen energy. Abash and myself have one represented life cycle assessment methodology, evaluation for greenhouse gas effect of hydrogen production groups in Australia. So that's another paper recently published. What is the CO2 footprint of that hydrogen I showed before, or any other means? What is, because ultimately you need to know the carbon footprint. So I'm going to talk about, obviously that's a background, technical evaluation, life cycle assessment, hydrogen as a system, some of the examples, and you can conclude kind of today's talk. So mainly I'm introducing hydrogen, all about hydrogen. Okay? So So you can see that a nice green forest. Actually, as I said, I was in Brunei. So I traveled from Melbourne to all the way to Borneo. Borneo is a fascinating place. Those people, I'm a Bengali background. You know, Vibhuti Bhushan Bandyopadhyay, one of my favorite writer. Actually, yesterday Avash took me to Rothenala. It was a Boy Mela. So that was the most. I said, I'm not interested in Mela. Maybe I can see, but maybe let's go to the Boy Mela. And I went there and I saw 2 volumes of Vibhuti Bhushan Bandyopadhyay storage, and volume 1, volume 2. And I couldn't resist. It's heavy, but still I had to buy, I don't know, $20 or something. So, but still relatively cheap, and I don't get it. And his story is fascinating. I mean, I think he should get Nobel Prize album. Maybe not obviously, no comparison. But Vibhuti Bhushan Bandyopadhyay is one of the best writer. The reason I'm saying that, there was another book, Hiramanik Chole, another novel. So those people who do not Bengali background, I don't know, maybe you will get that. But so that writer in the 1920s, 1930s, he represented the written way Bengal, essentially Bengal, because, and I doubt he may travel around in India, but definitely not outside India that time he went, because he was not very rich. And usually writers are like scientists, we are poor people, we don't have money to, unless we are paid by work, for work. So when I was, so that Borneo Island, so traveling from Melbourne, and then it's the whole Borneo Island, you have seen that one in the Southeast Asia, right? Kalimantan, which is sort of South Kalimantan, East Kalimantan, West Kalimantan is the Indonesia, and then Sarawak, which is Malaysia, Sabah, another Malaysian part, and Brunei, that's more or less Borneo Island. So the story that if you have anyone read Hiramanik Chole? Do you know the story? Maybe I have read it first. The main character is Sushil, and Sushil is a, that time landlords, Bengali landlords. So he's the son of the landlord. Not much, I mean, to get the money from the farmer and he live on. He didn't like that kind of life. So he came in Kolkata. He was sitting in 1920s. I'm talking about Gorema. You know that what they call that race course, isn't it? So he's sitting somewhere, and another character. His name is Jamatullah. He's a sailor. So he used to live in Meteorolus in Kolkata. So he was asking a permit for maybe smoking or something, and then he asked that where you are from. And he said that I'm a sailor, I travel around, etc. So, and then he showed that the Hiramanik Chole in Hira means gemstone, kind of precious stone. That's in English, obviously. So that's so he gave some clue that somewhere in the Borneo Island he know about an island where these treasures are hidden. So you need to go and explore. So he got excited anyway, and his cousin. So Sushil Shamut and Jamatullah went to Kolkata port, had some money, and then went to Singapore. And they describe about when they got into Singapore in a Chinese village. I stayed there also. And then they took a Chinese junk boat, went to Sulu Seas, and then Borneo Island. Near Borneo Island, there is one of the islands where they got a Hindu temple where the treasure is. Anyway, that's it. I'm not going to the story. If we say that, that's another matter. But the description of that island given 3, I think 4, 5, 6 pages. So I was reading, and and I was there, as I said last week. I've never seen that exactly. That the description of the trees, vines, the deep forest, the palm leaves, and the animals, etc. I don't know how the gentleman in 1920s, not going there, wrote that. It's a remote program, isn't it? So
similar for Chatel Pahar also.
Something like that in Mumbai. What's that called? There are some African Mombasa or something, isn't it? That
Mozambique like this.
So, it's like feels like that whenever we go in another state, we call it foreigner, isn't it? You are a kind of what they call Provashi Bengali, right? And when we go now another country. So, but anyways, that's what I was discussing. So, it's a fascinating Borneo Island as an island, still very deep, dense forest. And so nice and pristine and clean, and because it's not very populated on Kalimantan, because they have a lot of hydroelectricity, and potentially that can be exploited for making hydrogen. So, and in Bhutan, they call it Haze 3 or something like that, or Haze 2, it's hydro to hydrogen, hydroelectricity to hydrogen, because hydroelectricity goes up and down. And another country I worked is called Laos. So Laos has got a lot of mountains, and they have got a lot of rivers. Mekong River, you know about. So Mekong River has got huge amount of hydroelectricity potential. But Laos is a small country, they cannot consume that much. So they sell that electricity to Thailand. Thailand takes that electricity and sell them back during dry season. Wet season you get a lot of hydro, and dry season you get less. So can we manage that using hydrogen? So those sort of stories come into play so that you can regulate, manage. So anyway, so that Borneo Island always fascinates me, and I used to read novels, and now I've been there, seen there, and what's the potential of hydrogen? So that anyway, I'm doing hydrogen research, but these connections makes it really very exciting. And what's that story about H2? It's not new, because we are working with CH4 methane industry, natural gas industry. So it's a CH4, our chemist colleague, to H2, but there are some differences, right? CH4 and H2, we can get a lot of learnings from H2 industry, CH4 industry, but it's not the same gas. It's a low density gas, it has got a lot of issues, but on the other hand, a lot of potential. So we are thinking why hydrogen is important. Australian hydrogen demand could grow to almost 10 times current global production. And the production is 9-10 million ton by 2040. We think we will be producing 10 million ton hydrogen. We will be producing from, and the utilization is okay, heating maybe. Yeah, in fact, Australians love barbecue. So in our lab, actually, there is a hydrogen gas barbecue. So you can, test is same. It's not much difference here. So that's 54%, half, and then export. But as I said, I think I was discussing, we export a lot of energy to various countries like Japan, Korea, particularly LNG. And LNG, again, interesting thing. You know, LNG, liquid natural gas, liquefied natural gas. So essentially, LNG industry is not old. It's relatively new, I would say. Gas export, nobody can think of. But now, what we do is compress. So CNG, we have got CNG vehicles, right? So you can compress so that you can make the density high and also the energy content high, and then you liquefy it. How do you liquefy? Minus 152 or 153 degree. If you go minus, then you will make liquid at room temperature. So that's, I've been doing several energy plants also. So that's our about $100 billion industry in Australia. So we want to utilize that with liquid hydrogen, maybe compressed hydrogen. So that's the job, export. So because we want to replace, because Japanese said that we don't give lots of coal, that's what we do to Japanese. Lots of LNG, they say give us clean fuel, not with carbon loaded fuel. And that's the pressure from Japanese and Koreans. That's why we are working a lot on hydrogen area. And I believe many countries have their different drive, but in Australia we are doing that's why. And in domestic, we are talking about that's automatic, mainly hydrogen cars, buses, trucks, etc. 100% would be other use, industrial use would be 20% and 70% residential and commercial. So that's the way we are thinking that will be. I don't know what will happen. It's a 2040 is not far, but there are a lot of announcements, a lot of projects have been discussed, and that's why. Just recent update, because people are saying in the industry, oh, we heard government is giving billions of dollars. We had a lot of hype, oh, hydrogen, but it didn't turn into reality that much. So that's why still our resources minister, Honorable Benjamin King, on 21st May this year, she said less hydrogen hype is not a problem. It's just the next phase. Our ambition to develop a world-class hydrogen industry remains stronger than ever, she said. So still government supported, still government in it, and we are working towards that. So that's our CEO. We do a lot of mega trend analysis. Actually, there's an ex-CS, former CEO, Leopard News chief executive, Dr. Larry Marshall. So he was actually Australian. He did PhD in USA in Stanford, and most of the Stanford people becomes businessmen. So they even though they PhD. So but anyway, he came back and he took us. And he wanted to commercialize a lot of our technology and Wi-Fi, like say Wi-Fi. CSRO invented. We got every device Microsoft or other companies used to put Wi-Fi. We get for $5. So it's not much really. $1 billion. It generated trillions of dollars in the world, isn't it? It's just changed the whole world. So, but that's not satisfaction. We don't know. I mean, sometimes I feel some colleagues say, oh no, we should get at least $1 trillion from Wi-Fi. I said, no, if you put a lot of money, it wouldn't be that widely spread. People need to afford it, and then your satisfaction is that if somebody makes money with your ideas. That's the satisfaction of the research side. So we said that the drivers, global CO2 emission is going up. In the COVID time, we were running cars and buses, and so there's a blip, but again back up. So CO2 emission is going up, okay? So that's, we said 30 billion ton, roughly, plus minus, okay? So that going up 1992 to 2022. So we say that that's why the solutions are not the solution hydrogen. So this is 2020, roughly 90 million ton hydrogen already produced in the world, and that comes from natural gas used in the fertilizer industry, okay? Now, we are saying that we will go on 140 and then slowly it will go up. So our prediction, or this is international energy agency actually, many other prediction is that by 2050 there will be 660 million tons of hydrogen, and you can see that power generation, mobility, cars, buses, what's the other one, industry, etc., various things, and that kind of scenario. But hydrogen actually is not a kind of, you're not generating energy, it's a kind of conversion of energy to hydrogen, and you carry hydrogen. It's an energy carrier. So you may have an energy source, primary energy source, whether it is solar, whether it is wind, whether it is geothermal, whether it is hydro or biomass, etc. And then you convert that to hydrogen. So it's a carrier of energy. It's not necessarily generating energy. Okay. So now, if you look at that, so solar, they are saying $36 per megawatt hour. So that's wind is 38 megawatt, and depends wind is offshore, onshore, and within offshore there are low height or deep offshore, etc. Then I think these two made a lot of progress because of the cost reduction, and there are biomass which is still expensive, hydro is 64, and also geothermal. This is renewables, but there are, if you put nuclear, there is something not renewable but low CO2 compared to, so these things are happening, so we need to convert that to chemical. That's what we're discussing, how to do that. So this kind of, I think I have lived this, actually this was designed by Venkat Balasubramanian under my guidance, as I said, that South Indian student, PhD, doctor now, doctor. So we have got, so basically it's quite simple process in a sense. If a country has got electricity, whether solar or wind, that's the commonly we can see. If you have water, you make hydrogen. So basically you need solar and wind, some countries have good sun, some countries have good wind, and you need water. If you are, well, water is a problem somewhere. Australia is also water problem, particularly central part. But around Australia there is a lot of seawater. Like Brunei, I was comparing that Brunei is a very wealthy country because of petrochemical. Australia has got a lot of petrochemical. So now we move to energy transition, so that solar we get, and in Australia, solar electricity production at cheap rate, as I said, it's okay. Now, how we convert to, you don't have water, maybe fresh water, no, you don't have, but seawater there are plenty, and water desalinate using electricity and put in the electrolyzer, that's our key piece of equipment, and actually 90% of our effort last 5 years develop the technology at low cost. Many of my scientists, I recruited one South Indian, I think he's from Maharashtra. He is electrochemist. $50,000 I spent for getting his family into COVID time because I needed a good electrochemist. So now we were working on to develop this kind of technology. So if you put electricity, if you put water through that system, you will get hydrogen gas and also oxygen. And oxygen usually produces 5 times more than the hydrogen. And you can remember that COVID time in Delhi and many cities, oxygen, how medical oxygen also important. And I know our steel colleagues are using in furnaces oxygen also, potential industrial use. So that's why the story suddenly becomes pretty interesting, because based on electricity become cheaper, so you can make cheap hydrogen using cheap electricity, and at the same time you make oxygen. So that's okay, but how do you transport it, how do you use it, that's a challenge, because in this room, if you put natural gas, because natural gas is high density compared to hydrogen, you can hold more natural gas than hydrogen. but on the other hand, hydrogen energy content is higher. So it's a bit of balance, but on the other hand, the problem is that it is very low, it takes a lot of volume to, but that's why you need to compress, you need to make liquefy. And liquefying is more aggressive than natural gas liquefaction process. So that's what's the problem. So that's why we're saying, okay, we make hydrogen in Australia, plenty, cheap, just for the sake of argument, we make cheap. How do we send to Japan or Korea intercontinental transport? That's the challenge. So what we say, okay, let's take air from the nitrogen from the air, and you know lots of nitrogen is mainly air. Sorry, air is mainly nitrogen and oxygen. So you get nitrogen, you mix them up in the reactor, you make ammonia. And ammonia is already established industry. There are 300 million tons of ammonia transported around. Many ships, many ports can handle it. So you say, okay, let's send ammonia to Japan in liquid ammonia. So ammonia can be used as a, itself can be used, and somebody told that steel can be made using ammonia. You can refrigerate fertilizer. Urea fertilizer is ammonia plus CO2 together. Essentially, our body is 90% urea fertilizer because you know rice cultivation, particularly countries like us, all this is urea, and urea is indirectly nitrogen fertilizer, gives us energy when you take food. So the problem was that if I send ammonia, okay, that kind of use, but generally I want hydrogen from ammonia, use as a fuel or use as electricity to produce power. And that was a technology problem. So we have got enough technology, and it's quite late stage now, and or high TRL, so that we can crack ammonia gas to put through a membrane, and you get clean, nice clean hydrogen, which is 100% almost pure, and you put in a car, and you go. Basically, that's the way we have it. But it's still, it's a, so now, so many things we are doing. Desalinating, producing solar energy, and that means a lot of solar panels. It means a lot of wind turbines, a lot of steam, you know, and you produce that one. You do all sorts of things. Energy you need to produce CO2. So what is the net ultimately? You need to calculate that, right? And that's what the life cycle assessment technology comes into. What is the cost of that also? Because ultimately you need to compete with petrol, right? So that calculation, that I'll show you, that how to do that. So that's the part of this course section. So that's why that
each condition we will calculate.
Sorry?
We will calculate the each condition from
Yes.
solar to nitrogen
Like,
or
for
solar to
example,
hydrogen.
what's the desalination cost? What's the electricity cost? What is called levelized cost of electricity? Have you heard the concept? Levelized cost, that means
Generation cost.
capital cost included,
Huh.
you know? So then you get the hydrogen cost, then you make the ammonia production cost, you transport everything, so it has to be cost effective, right? So that needs quite a bit of thinking and kind of new skills that I would say. Not necessarily completely new, people know, but you can adapt that.
Sir,
And yes,
so what's the smallest unit of hydrogen production that can be done practically?
so this one is
Smallest
there, for
unit.
example, 20,000 ton per year.
This 20,000 ton
20,000
per
ton per year, I would say it's a smallish.
like the
10,000 is the small, to make 10,000 ton of hydrogen per year.
10,000 ton per year.
It's
So
a small plant.
approximate the cost.
You could be 100,000 ton, more bigger plant, cheaper.
Like sir, the setup cost, the capital cost to install that
So
10,000.
that's all these modules. You can have electrolyzer cost module. And that at the moment it's $1,000 per kilowatt or $1 million per megawatt, but that is going down. Like solar used to be very expensive, right?
Yes.
It is going down. So that's the way. So basically, Venkat's PhD, when he came, I said develop a diagram like that. He did, and I said, okay, now develop a cost model, digital version of that. Actually, we have got each hardware we have got, and we tested, we kind of have lots of data. But digital version of that, essentially, there is a cost model of desalination, cost model of solar, wind, etc. So we can basically plug in and all these calculations down.
Software. You develop a software for the calculation.
So this sort of software you can use as Pentex, Sima Pro, L03 experts, but not necessarily software, but software gives the information and ultimately you have your own tool to calculation. So that's what we have developed. Okay? As part of that, I showed the two thesis. So one is that's the Venkat's essentially. So far, any question?
Can I moderate a little?
Yes.
Sir, if you look at the release of oxygen along with the hydrogen, we have a typically beautiful application in steel plant. Oxygen is blown in EOF converter as well as in the blast furnace. And we are talking about hydrogen technologies. Perhaps if you have an electrolyzer releasing hydrogen as well as oxygen, oxygen can go to this blast furnace and EOF shop. Hydrogen can be used in blast furnace or DR. So there is typically clear pathway, but people are not exploring that kind of commercial applications.
Right, yeah. So I think that's, so when you talk about strategies, solutions, it's not simple. I'm saying that if it is simple, people would have done it. There are
No,
challenges.
not that simple. Once we combine oxygen and hydrogen in a blast furnace, that's not a simple procedure.
No
Yeah.
one told about combining.
But
separate-
that's right. So,
separate
but at least you have a product.
We are
You have good
basically
skills.
taking a precursor for explosion in the blast
Yeah,
furnace.
that's right.
No,
So,
you have misunderstood. I'm telling about injecting oxygen in blast furnace is already happening.
Yeah.
Injecting hydrogen in DRI is going to happen.
Yes.
If I have an electrolyzer which is having oxygen separate, hydrogen separate, we have different applications separate. We are not combining.
so oxygen can go, you say basic
Yeah.
oxygen furnace, hydrogen can go to blast furnace or DRI, something like that. You see what I'm saying, right?
Yes,
So,
yes.
so now tell me here from the skilled colleagues, what's the biggest challenge do you think? For this sort of
using-
hydrogen application, see if I want to produce
Using
that
hydrogen
line
steel.
from here, haze to, or haze to from here, whatever, goes to a steel plant, what's the problem?
No, the problem is the present technology of blast furnace is not compatible to use hydrogen. That's
Right.
the first thing. Because we cannot put hydrogen directly into the blast furnace like that. The technology has to change completely.
So
The
that
DRI
could be-
is one of them.
That could be DRI, that
Yes. So
potentially.
the blast furnace, first the blast furnace would go.
Yes.
No,
The
no,
technology
blast
would
furnace
not-
need
It will
go
be suiting the
correct.
blast furnace.
Yes.
No, no,
Not
let
the
me
current
correct.
blast furnace model is.
Unless
The
it changes.
technology is already available. People have not installed that. Let me
That
tell you.
is what he's
See
talking
this,
about is it's a pilot scale, very small
That's right,
scale.
small
No,
scale.
not pilot scale.
So,
Let me
so
take you to the
do
history.
you, are you aware of the big plants somewhere?
Yeah. Polworth has got a technology of injecting hydrogen into Polworth.
What is the custom
What
one? They
has done
We
started
have
the
not
experiment
purchased-
few years back
Yes.
with single tuber.
yeah,
No, no.
5 to 6,
That's
6
only,
to 7 years
that's
back.
only
I think.
preliminary study. People started approaching into
So I think my understanding is still everyone
It's
is
very nascent stage,
installed
very
at
nascent
small
stage right
scale
now.
and testing and learning. Maybe down the track
Yes,
it
yes,
is.
definitely.
No, no.
And that
This technology is running in Mexico.
Mexico. But anyway, in China, I can tell you, last TMS, even 1 year ago, last TMS I myself and Avash went to Las Vegas. Before one, that was, I can't remember, one US city, maybe San Diego, I cannot remember. So that place, TMS, I don't know whether you heard of, 4,000 people, 5,000 people get together, talk about, decarbonization, etc., of the industry, metallurgy. So there was lots of presentation, there is a hybrid technology that, so that sample I saw, they took that one, they market a small piece of, this is still made of hydrogen, something like that. Small, very small. Still, finally one guy presented, a Chinese professor, okay? He presented probably half an hour, I think it was a keynote. Unbelievable amount of data, blast furnace, injected, and then we asked, who are you, kind of, and his English is not very good. So, he, in China, it was different. He is a professor in a university, I don't know, one of the Beijing steel university, big, therefore, steel, a specific university. He is in charge of 10 million ton steel making plant in China. He is the chief technical officer of that. In China, they do that one. In their academic put in. His role is that he is the CEO of the steel industry because he is the expert. Technically, it doesn't work here. We employ CEO goes to the there. So then that guy, the amount of data he showed, he injected. Is it not a problem? We can do it. Maybe the economics, maybe the supply of hydrogen. We need big amount of hydrogen. Who is going to produce that? Last year in China, 300,000 ton of hydrogen globally produced, green hydrogen, out of that 90 million ton. So it's minuscule, right? 280,000 ton out of 300,000 ton produced by China using their green power. So they have got already megawatt scale electrolyzer. So it's happening, but I think we didn't know about China because we don't have much intelligence. They know about us, we don't know much about them. We thought nothing happening. Suddenly we saw that a lot of activities coming in. So my feeling is that if they can test and commercially they can produce, other people will follow.
We are talking about green hydrogen.
Green hydrogen.
Yeah, green hydrogen generation is happening.
Yeah, green hydrogenation happening and he's testing in blast furnace.
Yes, that is just
That is in the
research
secret.
stage.
Exactly.
In the same stage.
So research stage.
Yes.
So he's sort of putting and
Yes.
getting collecting a lot of data in the
Yes,
long
yes,
term. So it's a, but even I couldn't imagine someone putting through the tuer the hydrogen in a blast furnace. It's you can't make this decision, right? No, even in Western world, nobody makes this kind of decision in the industry. But Chinese, maybe he has got the power, or he has got the. It's a one, that sometimes that works. But I can tell you that we have a lot of data. And that's the best data so far I've seen that on hydrogen in blast furnace trial.
Actually, putting hydrogen into tuers is fatal error. We have to put in the area where the hydrogen is helping in reduction. So Allworth has got the technology of injecting hydrogen right at the reduction lower stack.
So
The technology people have not purchased because they are biased with some OEM. There are some cartel.
and also it's still expensive. I think my feeling is that
It's still
supply of
cost,
hydrogen, supply of because you need a huge amount of hydrogen. Who is going to produce that? Now Toyota has got a hydrogen car, and people are suing them. Oh, you sold me car.
Where is that?
Where is the hydrogen I can refill it? That sort of thing. So that, anyway, that's the question. So it's not a big deal. You can see that one. Making, as I said, it's a simple. You've got solar. You put through anode and cathode, and it's kind of membrane. So if you look at that diagram, so I can say, so that's the kind of splitted, water is splitted, and you get hydrogen coming out of that. So that's the hydrogen, and that's coming out of that, going to a fuel cell, and you get oxygen, you get power. That's kind of very basic form. And if we we have that. So basically, that cathode, anode, if you give the catalyst, people can make, and then what you call membrane electrode assembly, and then put in a stack. And so you have a system like this, all solar directly connected. Actually, one of my students is doing it. And hypothetically, we can talk a lot, but actually, if you do that solar goes up and down. Okay, although solar has got nice day, etc. Good. If it is wind, it's even more erratic. So can electrolyzer handle it? What's the response time, etc., etc. And that's we're talking about. There are varieties of electrolyzer. One is PEM electrolyzer, we call it. That's our specialty. But we have got solid oxide electrolyzer. So here, feed is the water as a kind of water is goes through and split it into. But if it is steam, you get more hydrogen for same amount of electricity. So say this PEM electrolyzer, 55 unit of electricity required to make 1 kilogram hydrogen. Okay, whereas solid oxide electrolyzer you need 33 or 35. So you drastically reduce, but you need to supply steam instead of water. So you need to have some
Steam has also required that energy.
energy. But say you're in a steel plant, you may have some waste heat, free heat. Let's make steam, free heat. That's one way. Second way, that CO or your blast furnace gas, there are other solid oxide fuel cell. You can generate CO2 to CO, and then CO can be. So some of the CO2 can be broken into. So these are kind of electrochemical systems, electrochemical technology. We have all that. I mean, like a battery, same thing, energy. So you have got EVs nowadays everywhere. You can see electric vehicles, right? Who is going to charge that long time? Say you are driving from Kolkata to Delhi or to another long distance. How many times you can charge and how long? With hydrogen, you can put in like a petrol station. You fill it out and you go. So that flexibility becomes important sometimes. That helps that way. But the challenge is here also that to make hydrogen industry viable, you need lots of material and lots of even we are talking about solar and wind. Why suddenly that geopolitics become very difficult because China controlling turbines or renewable magnets and tariff, and China actually is using that rare earth processing to negotiate with US. The reason is that if you are talking about energy transition, but where even lithium, where the lithium can processing discussion, lot of people have visited. That's where I can give you. So if you talk price, we are. So this is the price. This is $1.6. So this is all these zones. This is the highest. It looks like Australia is a pretty good country from this range. Yeah, maybe parts, some parts good. because we have done that calculation and real. And now, where there is a particular plan, you can see this is the kind of solar coming from the south. I make solar and wind, I get like our power plant efficiency 80%, I make it this 40% solar, 25% together similar kind of. Okay, so that's put a bit of a storage like 1%. So a lot of going to Japan, Korea, this kind of countries looks like even Middle East. So it looks like Norway. Someone told me about you told Norway, right? So they are. So it's happening. It's not America. California looks like there will be some activity. So because these are the cheaper area. So that's what is moving around. That's what calculation is happening. But again, these are chief scientists. Actually, we were got the fast hydrogen car. There are maybe 20 cars now in Australia, hydrogen cars. There are 3-4 buses. There are trucks also. So that so he sort of we call it hydrogen man. So he convinced the government hydrogen is the goal, and government invested a lot of money. So that but on the other hand, have you heard these terms called green, gray, purple, blue? Hydrogen has no color, no order like that. But they call it the green hydrogen is a clean hydrogen, basically from renewables, zero CO2, nearly zero CO2. On the other hand, black hydrogen from coal, brown hydrogen from brown coal, black coal, brown coal, grey hydrogen from natural gas. Currently, I said 90 million ton hydrogen is produced. 97% from that, maybe majority from gas, some from black coal in China that use it also. So, but hydrogen is not sold as a product. It is used within the plant. That's why you don't see as a product. And then you can have pyrolysis. You can have a pink, even yellow hydrogen that we mixed or green. I think nuclear is better, pink or purple. And another thing, nuclear is another interesting story. Because nuclear power plants, once you start, you have to run. You cannot just go like that. Okay. So now you may producing it, you don't have demand. How do you manage that one? Then hydrogen can be a bit of buffer solution at the same time to run the plant full speed. So that would be cost. When is it? So that's the cost is not a problem. Cost is at what point in time? Is it average cost? Is it yearly average? Is it on the time? So those sort of things need to be calculated. So that's the cost. So at the moment today, it is like say $4, $5 US dollar per kilogram, plus minus in Australia we call it a little bit more because conversion. Target in the future is below $1 US, plus minus say $1.50. Okay. So now where this cost reduction possible? So 80%, if you produce electrolyzer, 80% cost reduce, still you will reduce a bit. Electricity cost $20 per megawatt hour US dollar from 53, then you can have a cost reduction. So electricity has a big role. You electrolyzer efficiency you can improve, but small bits and pieces in the work, you know what? Weighted average cost of capital. If you borrow the money from the bank, that 10% you can borrow interest rate, you can borrow and say that drops to 6%. Still you can have some benefit, but these benefits are smaller. You can see. The majority of the benefit is the electrolyzer production cost you need to reduce. You need to also reduce the electricity cost. Make sense? These are the two important variables we need to deal with. If we have cheap electricity, if we have cheap electrolyzer, we have a still. So that's what it says. The power cost is 70%, electrolyzer is cost 30%. Generally, water is 1 to 5%, and pretty good. Water is not a significant problem. But if you have water use, lots of water use, and suddenly you go and need water, 9-10 liter of water required to make 1 kilogram hydrogen. So it's not a big amount compared to other industry sector, but whether people will be allowed to give it. So in that case, maybe desalination if it is only at a cost. So we say this is our calculation, say those calculation. So somewhere in 5 now, US dollar per kilogram. In 2030 maybe 3, and then maybe by 2050, 22, and that's why we're saying 2070 onwards, maybe that is story for steel making is okay. So that kind of thing. And you need to compare with other fuels also. So that's conventional hydrogen, renewable, low hydrogen, and renewable hydrogen as a kind of how they're progressing with the cost. So far, okay? Are you with me? Clear? Now this is really very interesting concept, and this is a completely new concept. Nobody at the world So actually, fortunately, that LCA team I say, we are one of the best teams. I can claim that because I've been around, I've seen around what other people are doing. And same with this kind of cost calculation. So people often call, say $4 per kilogram. It is average maybe, but this is our electricity profile so in Australia, electricity is costed every 50 minutes interval, okay? So this is hourly generation profile, okay? And hourly electricity goes up and down, you know, solar mix, all these mixes, our cost goes up and down. Here, I don't know, is it a fixed price all the time or it goes up and down?
For last consumer it is fixed, for the end consumer it is fixed, but for the generation plants that we sell it to the distributions and all, they vary between 15 minutes.
So that's where that point we're talking about, and actually our end consumer in our case also similar. So but I'm talking about the large generation retailer, kind of those people who are taking electricity from the power producer and then going to the next level, next use. So that goes up and down. So if you feed that cost and you feed behind there is a hydrogen cost model, it will calculate like that. So some cases you can see that very high cost because those times electricity cost goes to the roof. And some cases you have got lots of times there is a negative electricity cost in Australia. Nowadays it's a bit problem. You've got lots of solar surrounding, lots of wind during daytime, night time, maybe even wind, but you don't need that much demand, so you dump the electricity. I've seen that 60, 70 megawatt plants, they're dumping electricity because they are no use. What can they do? You can't put in the grid. So maybe those times, how much that distributed and that dumped or kind of unusable, what we call curtailed electricity or excess electricity, sitting in the system. Because at the end of the day, that electrons, you take that electrons, convert to chemicals, make hydrogen, your story may be better, right? That's how you tell the investor. Same with in Australia, tax incentive. So that's the red line is the previous same line. Now, if you put tax incentive, that will drop down a bit because these times of day, maybe the hydrogen will be sometimes, because it's depending on the grid, hydrogen will be very low CO2, sometimes it will be high CO2. So those times low CO2 you get the benefit, when there is no, you cannot get benefit. So companies are trying to say, okay, let's do that yearly calculation, but government told us what's the best option. My feeling is probably it should go on because that will government, because ultimately it's government money. So this sort of decision here will come because they have got an incentive system, I think they are introducing, right? So we don't want to lose industry. On the other hand, we don't want to give unfair benefit which is not required because they have, so should we, I think we should probably look at their energy production and see whether that is clean enough or green enough, that time you give incentive.
So what is our main purpose? Green hydrogen or to make hydrogen?
I think clean hydrogen is immediately to get an industry, maybe we need to be compromised, but slowly.
Because till now the scenario is not ready for the green hydrogen.
That's why I'm sort of green. That is green, right? Normal green. But ultimately, if it's not clean hydrogen or green hydrogen, what's the purpose of doing it? Plenty of coal, plenty of gas, running very nicely. We're doing it to decarbonize, right? So I think we should aim for clean and green hydrogen. At least clean hydrogen, when I say clean, it's low CO2. It can be various ways. It doesn't have to be just renewables. There are other ways to
So
make hydrogen.
is nuclear plant generation is considered as a green energy or not?
Nuclear, I would say low CO2 footprint because that's another story. I don't know how I'm going with time. I need to be careful because when you talk, I cannot remember the thing. I can talk for hours about these other things because some of the things I've done myself. And so you know that nuclear energy, right? It's a lot of discussion. Fukushima, have you been to Fukushima? I've been to Fukushima. Okay, so that. But anyway, that's a different story. So I think 2012 or something like that. Our Australia, because Australia produced a lot of uranium, there was a bit of voting or opinion that maybe we can have nuclear. So we got a big project. Look at the CO2 emission of nuclear. So we did that study. Actually, original study was done 4 or 5 in the 70s in the US. Look at actually CO2 footprint of nuclear. And there are thousands of papers, you will find it. Most of them is copy. So okay, let's look at that. So we looked at that and looked at kilogram of CO2 per kilowatt hour energy sent out from nuclear. And definitely it is small. But it depends uranium has a role because more poorer grade ore, low grade ore, which is happening now because good grade is going on the market, you do a lot of upstream processing and mining. So that analysis, it could be, if it is low grade, super low grade, it would be similar to gas. What's the point? That's number one, it's a CO2 point of view. Second is waste. So I saw that in Japan, so that Fukushima, so that's why that main reactor thing happened, about 50-kilometer zone exclusive. So I don't know, Japanese do not tell. We are there G20 country event. G20 means the global 20 countries. Indian colleagues are there from Kerry also. So I represented Australian government and Australian one. So they took us in a bus and then we had to go through that because 1 hour drive through the place, we didn't have choice. And I said, why? But anyway, the communication, some European colleagues are very kind of upset, or we are going through the nuclear because we get radiation. If you go through that, it is really a movie set. No one there, it's a ghost land. 10 years, all these houses, deserted, locked, and creepers, weeds, and the trees are taken. So nobody lives there. Every now and then you will see some people with a shield, kind of wearing shields, taking the soil. I think they are up to some level, putting in a radioactive bins, etc. So it's a $40 billion. I think I heard that investment going on, and I don't know how many in the future. Because 10 years they had to evacuate the place, and slowly they're reducing that content zone. It's still probably 20 kilometer or 15 kilometer line. You cannot do much. So, but when you go through, you feel like that these are people's livable house. They used to live there. Emotional toll. Suddenly you say that you cannot live in this house for 10 years or 20 years or whatever. You cannot come back. If something goes wrong, I think that's. Although I know that technology is becoming safer, but in Australia there was a big debate. For the last election, our Liberal Party and Labour Party, like Liberal is current government is kind of, I would say, Labour is Liberal Party is conservative. They took nuclear stand, and current government against nuclear. They are pro renewables. So the Liberal Party lost very badly. In US it's maybe different, but they said that they wanted to market it, but people didn't like it. So we produce a lot of uranium. We send around the world, but we don't want anything in our backyard kind of that mentality. I mean, that's not always 100% right. Maybe we need to have a mixed kind of view. But nuclear is not. If you have renewables, you have lots of land, you have got cheap electricity source. I think for Australia, because we have to invest now, there is no skills. If you do now, it will be 20 years down the track. Nuclear is still expensive. It's 4, 5, 6 times than coal. Its running cost is low because but uranium price goes up and down. Now it's $100, I think, because suddenly a lot of countries thinking about nuclear. Uranium price is up, so $80 per pound or something like that. I mean, $100, $100 per kilogram. So that means you need also a higher cost. But at the end of the day, my feeling is that mining is a problem because you mine radioactive material and then waste is a problem. Although waste is still, one source system. So anyway, so if you Google CO2 footprint of nuclear power plant, I think our paper is one of the paper that we use. So that's just very important. So it's a solution, but not it's the complete solution.
So India is the same scenario. India don't want to be in nuclear power generation.
But I heard that a lot of people are talking about small scale, modular, etc., etc. But again,
there is a test sort of that.
But I know India has got a thorium. That's maybe another. That's why India probably wants a little.
Thorium is found somewhere in India.
Many places.
Yeah.
So maybe around that. So that's the thorium is more. They are talking about it.
Yeah, thorium which.
So when we talk about calculation, I need to be mindful of time. So CO2 equivalent, which we call it, because 1 unit of CO2, 1 unit of CO2. Because 1 kilogram CO2, if you are emitting 1 kilogram. If you are say emitting 1 kilogram methane, okay, what is that CO2? Do you know how much CO2? 25 kilogram or 28 kilogram. Because methane is 28 times. So CO2 is benchmark or scale. Methane is 28 times. So some people say, okay, I don't emit any CO2, I'm green, but I emit 1 unit of methane. So, but then if you do calculation, it's it's not only you say that I'm not CO2, you are 28 times more bad. Similar with nitrous oxide. If you produce 1 ton of nitrous oxide, 300 ton nearly CO2. That we call it characterization factor. Then actually that was I think one of the examples I found that technology, they market very nice, green, clean and etc. And then said, what do you use? Say one of the gas is SF6 sulfur hexachloride. SF6 is, do you understand, give me any number, how many tons or how many times of CO2 that would be SF6? Any idea? Give me a number. Any number.
Thousand.
Increase more. 10,000 more. 60,000. It's a bit more, but halfway. So 26,000 times potent. So if you need 1 unit of so that these are the gases. This is SF6 that one. So these are the greenhouse gases. CO2 1. This is 28 times CO2. That is 300 times. HFCs, PFCs, perfluorocarbons, NF3s. But this one is the one of the potent gases. So how we calculate? We call it. Having this concept, anyone familiar with scope 1, scope 2, scope 3? You are, right? So scope 1, it's like whatever happening within your system. So that's a company facility, that vehicles. In India, I know you've got captive power plants, it's called, is it? Your own power plants. That will be your scope 1. Okay? But if you buy electricity from the grid, that's the electricity, heat, etc. Electricity you buy, that's called scope 2. Okay? So, and scope 3, everything else, like materials, chemicals, your people travel, employee travel, that sort of thing. So these are all upstream. Similarly, you have got downstream. You have got a product still coming out of your plant. You transport it, use it. That's called scope 3. Indirect. This is indirect. This is indirect. Scope 2 is electricity purchased from the grid. Is indirect. That's the power company. So you guys both are here. Your power company and a steel company, for example. So you give scope 2 to a steel company. So you are scope 2 for a steel company. Okay. Do you understand this kind of system?
Right now we don't take into account scope 3 for our internal calculation.
That's right. So, but scope 3 is also some, like NIT Durgapur. What is their emission? Their emission mostly students and other things. A lot of scope 3. There are ways to calculate. I will do that. I'll tell you probably more later. So, but essentially scope 2 and scope 1 people are most interested.
Scope 2 is the highest.
Scope 2 has because of the energy companies. Yes, so that's right, because they use carbon. Now, when we say LCA, life cycle assessment, because life cycle assessment is direct plus indirect. So we call it boundary. So it's called gate to gate. It could be cradle to gate. Cradle means start to gate. Here are my product. So cradle to gate, what is the footprint here? And it could be cradle to cradle. The product goes out of the system, so the car or iPhone or whatever, or steel, you use and then finish and then end of life you go back. So that's the whole cradle to cradle. But most of the LCA done, it's called cradle to gate. Here we finish, and so that one, the definition would be scope 1 plus scope 2 plus scope 3 upstream. That's cradle to gate. Is it clear? Most of these are like, what is the CO2 footprint of steel? I'll calculate here, so I'll calculate scope 1, I'll calculate scope 2, this is the electricity component, and then scope 3, everything else, but we have to calculate. But there are ways to calculate.
For the steel production, if you want to calculate, you are saying that scope 1, scope 2, scope 3, all 3 components should be combined.
In LCA. Because
In LCA.
In LCA, you need to know what's the 2. Because it maybe steel plants, it depends on the product. Some product is we know that on scope 1 and scope 2 to count, 95% we have counted. But some processes, some product, maybe chemicals is different.
Chemicals are there.
Sulfuric acid is produced somewhere in China, maybe, and they had carbon in it.
Lime is the input product also.
That's the way you need to do it. And then another thing, if you know that, at least you can, it's not necessarily somebody is giving sulfuric acid with high CO2, another one giving low CO2. It's not necessarily that one, but I can tell you, man, you are giving sulfuric acid to my plant, it is a high CO2, can you do something? So it's a kind of educating each other, and same thing with downstream also, because you might be liable for their product kind of that way. So that's how it is working.
So suppose one chemical I am using in my plant.
Yes.
So we are calculating some CO2 emission for producing that chemical. Then if that chemicals may be produced in India China.
Yes.
Okay. Then when we calculate that chemicals which is used and produced in India, there will be some CO2 emission.
Yes.
And if that chemical is purchased from
Another
outside,
country.
another CO2 emission will be added there,
Yes, they have to be
transported it.
transport, and because that emission from that chemical plus transport,
Plus from-
shipping would be
And
added.
considering the total CO2 emission for producing that chemicals are equal,
Required.
if we calculate that transportation CO2 also,
Would be transport to be added, which is shipping, number one. Second is that two countries, when chemicals are made, their electricity profile may be different. Maybe some country will be high CO2, some country will be low CO2. So that's why suddenly it becomes very complex and complicated, and countries are fighting that what is called carbon border adjustment mechanism. You know, under
But that country is producing the chemical, so in their calculation the CO2 emission is done.
calculated.
So and we are paying and we are purchasing. So just the transportation part should be added in our profile, not the whole production process.
Chemical part depends on how much. Say 50% chemical comes from China, 50% from India.
Right.
So then
I'm talking the 50% from China.
Yeah.
That's for the such example.
So that way you divide, but if you say 100% chemical is used in here, then you don't have that one, if your question is that. Yeah. So it depends how you, basically it's accounting. You have to trace an account and go through the supply chain, who is producing, that's the net transparent. That's why engineers love it. Number, each has got a number. So you have got a quantity, you have got a unit. So that's the beauty of this here. Okay? So I think I'm sort of finishing probably, I am finished also. So that's kilogram CO2 per kilogram hydrogen. 1 kilogram CO2, what is the kilogram hydrogen? 1 kilogram hydrogen to produce, what is the CO2 footprint? Because 1 kilogram hydrogen has got 33 kilowatt hour of electricity in it.
Required.
No, it's required 55. But the energy content of 1 kilogram is
Its
33
its
kilowatts.
efficiency is
It's the
60%.
energy content, you
So
can say.
you are
But
saying
if you-
55 required and 33
They already lost some.
22 we lost.
Yeah, you lost. Yeah,
20% loss.
Lost, yes.
40%.
But it still say if it comes from renewable, who cares, you know? That kind of mentality. So now, that is in Australia, actually, that's called Frontiers in Energy, we published. Actually, that's RD20, I told you Japan, I went to Fukushima. That RD20 called Research and Development 20, G20 countries. Japan is the previous Shinzo Abe, I think Japanese Prime Minister.
Shinzo Abe.
That. So he sort of, that 20 countries got together. It's a very good program, and I was the co-chair of this LCA for hydrogen with another scientist from USA, Urban Lab, Dr. Amgar. So two of us brought all these 20 countries and then said that let's talk about how to calculate CO2 footprint of hydrogen and give the methodology to the world. And that was, I think, so we, each country contributed a paper. I don't know Indians did that one, but anyway, they contributed in other ways. And then we published in a special issue, and then this is our Australian contribution. So what we say, that CO2 footprint, you see that one, scope 1 emission, scope 2, scope 3, I said, clear? And then another thing, biogenic emission, or called fossil CO2 or biogenic CO2. If it's CO2 coming from biomass component, and if that biomass is replanted, we assume that's a neutron, CO2 neutron, because you are cycling CO2. If it is fossil CO2, that's what the problem is, carbon fossil, that's the problem. So scope 1, scope 2, this is important, and scope 3 we consider, as I said, scope 3 is difficult. So if you say grid connected and PEM electrolyzer, so what are electrolyzer or technology? So Australian grid at the moment, in Australian grid, if we feed to the electrolyzer and make, it will be 45 plus 47 kilogram of CO2 per kilogram of hydrogen. It's very high, right? Then you have got grid connected alkaline electrolyzer, different type, black coal gasified and electrolyzer, and scope 1 is the black coal gasification process, and then scope 2 is the electricity you need to process. Then you have got brown coal gasification. Then you have got various ways you can make hydrogen, okay? And you can see that one coming down. This one is biomass to hydrogen, and you can see that a lot of biogenic CO2. Here I don't biogenic CO2 is, but still we have showed that one. This is neutral, but this one is a component you need to worry about, okay? You need to mitigate, etc. But if you look at, this is the solar PV. This is solar PV, alkaline, PEM, onshore wind, offshore wind. This is almost nothing. So now the hydrogen company is coming. Okay, there is no direct CO2, but for making wind turbine, making solar panels, you need a lot of steel. There is a CO2 component, right? That we have now calculated. We have got a model that calculates that one. How much steel required, how many diamond required, how much magnet required. So this is kind of well established. I think Americans are very good at that. That our lab, GREET, they call it GREET model, and that we have customized. We have used our own model also. We have developed. So that Argonne Lab LCA team and our team, I think we are the one of the two best teams in the world. There are other people working on, but US, they started long time ago. There are 20 dedicated scientists working in this area. Our number is a little bit less, but we are more or less on par. So that's how we calculate.
In that case, how will we calculate? Because for a solar panel life is 20 years. One panel will run along for 20 years. So do you need to divide the 20 years life?
Everything you have to take into account. That's the interesting bit. Yeah. So we developed a model, lifetime, making of solar panels, silicon production, and that's the, so LCA, really I get fascinated because I didn't know enough how to make silicon. So, but anyway, for another purpose I have to make silicon industry, and Australia produces 100,000 tons of silicon per year. And, but silicon, for making solar panel, you have to have high lines, very, very high purity. How much energy, how much electricity, where the electricity coming from, all these have to be put.
So same should be for our thermal plants also. Because thermal plant, the raw material is coal.
But you have got other structure, etc.
Yeah.
So that's why when you do LCA, actually Avash will give you the demo version, you can play around. It says infrastructure included or excluded. If you include, that everything will be counted. But generally, most of the processing infrastructure does not give that much. But if it's a large solar plant, large wind plant, it's a nuclear. You need to have a lot of decommissioning. So that's why these are, it's case by case, it's a judgment, it has to be sound, it has to be
But the model should be approved by all.
Yes.
The calculating model should be approved by all. We are calculating on the one methodology and other is calculating from the second. So we cannot compare the
So that's why now standards have been developed and all these countries, the best people, from the best minds from together.
G20,
like G20, mechanism, etc.
So the norm should be clear.
It's becoming more streamlined and more uniform, but it was a problem before. So different models and etc. So that's why when I say, so about this particular grid I showed you before, the same grid, Tasmanian grid, so, because I'm picking Tasmanian grid because it's a lot of hydro electricity. So it's again, but it has got, what happens, we have Victoria, Australia mainland, Melbourne where I come from, south part of Australia, Tasmania, 400-kilometer distance on the sea divided by the sea. We have got a high voltage DC cable, HVDC. So that's what we call back to back. So basically 400, 500
400 kV.
Yep, that's right.
400 kV.
400 kilometer distance and 450 kV also.
kV.
So that can go both directions. So if the dam is
Through the sea.
So the under the sea. Yeah. So if it was probably $2 billion we spent, but initially targeted was less than $1 billion, but it cost blowout, what happens in the project. But anyway, eventually we got it, which is a good thing because when the dam is low, we have less electricity in Tasmania. Suddenly
You transfer this.
coal goes, then becomes dirty electricity in the sense we call it, because CO2 footprint goes high. On the other hand, if there is more, then it can go back to Victoria. So, but most of the time we give it to them, they don't give us because that hydro is so. But anyway, so and also there is gas. So gas, hydro, but again they have put on solar. Now a lot of wind coming. So some of the days, you see the CO2 footprint is very low. So those are the times. So we say that if you want to really make clean green hydrogen, make those times. Whenever you get, you make lots of hydrogen. So your clean hydrogen, so that's the way. But if you take average, it will be 5 kilograms CO2, 5 kilograms hydrogen. And that 5 kilogram includes electricity component, includes the electrolyzer component also. Because electrolyzer to make it also. So this calculation has model behind sitting, and that's our IP, that's the way we have developed, so that feed and generate this data. Does that make sense?
So by that logic, hydrogen should be produced in the daytime only. For the India, if you
It's
say
not necessarily daytime for solar,
and wind.
but wind is nighttime. Wind nighttime, isn't it?
But it's not counterbalancing. Solar is way higher than the wind. So it's not counterbalance.
It depends, right? So that's the message I want to give. Sometimes people think simple, but it's not simple, isn't it? It's so many factors, so many variables acting together. Alright, I'm towards the end, I think I'm not sure how we're going to finishing. So there are, the turbines, forklifts, there are this sort of, so one hydrogen car has got 5 kilogram tank, it can take you to 700 kilometers, something 500 kilometers, but now 7 kilogram tank there is. We have got buses, that's in South Australia, we have got Toyota Research Center, this is all, we have got 3 cars, this is one other car, you can see zero emission, zero CO2, another car, I mean now 20 cars, I think I've seen start to finish all of them in front of our own eyes. Australia has a lot of hydrogen cluster demand, big facilities now happening. It's a decent development. Globally, lots of countries are doing, hydrogen studies. India is getting later, but that's quite big. That's our refueling station. Actually, we have got a refueling station. We can refuel 2 cars a day. That's one of the gentlemen that FMG talked about is the owner. He invested $50 million kind of discussion. This is how you inject hydrogen. There's another car. This is we have got 2 refueling stations. This is one, and the second one is ours. But in Australia now probably 20 refueling stations. In Korea there are probably few hundred. In Japan they have a target 1,000 by 2030.
So how much will cost you for refueling?
1 kilogram, $2 they the target, but they sell in say California $15. In Australia maybe $14. So $14 per kilogram.
14 Australian dollars.
14 Australian dollars. So 5 times 14, $70.
$70.
And then you get 500 kilometers. And if you buy
It's
$2,
cheap,
60 liter petrol, I pay $2 petrol, so around 120, 100 $100. And it will take me probably around that same 700, 600. So its cost wise not much. It's the production of hydrogen and the cost of the car is expensive.
So for the 20 cars, you have 20 stations.
Yeah.
You are saying the 20 cars only in Australia, you have 20 stations.
Nearly 20 stations now, I think.
For the
But
20 cars.
buses, we have got buses, we have got trucks also. So there are a lot of trade of ammonia. I think I'm moving fast. This is one of our technology in Europe. They're commercializing 100 kilowatt system now in the world. That's I was talking about. So you can get ammonia and hydrogen, and it goes through the gas, goes through, and then pure hydrogen you can take it. It's a membrane process. What else? I think there is a system. It's called Labo system. So I sometimes say, I don't know, do you have the dry fish village in Sundarban or in some parts of the countries like that? You don't have nothing here, so there is some power, there is everything, and then you can have system like that. So yeah, this is one technology solution, the other challenges, technology mixes, but you have to customize for the company. I think we'll finish it here. Tomorrow we'll come back and show you few quick snapshots of this renewable technology, and then we can move on to the next module. Okay? How does that sound like? Okay? So far today, I think maybe tomorrow we'll recap some of the issues and discuss a bit more, rather than I just talk. I don't think no possibility of. Okay? Alright, have a nice day, so long day, but at least we will establish some relationship. Now we can go from there.